Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're going to cover Chapter 5 for our MCAT Organic Chemistry playlist, and this chapter is titled Alcohols. In this chapter, we're going to cover the following objectives. First, we're going to discuss the description and properties of alcohols, including how they're named and their physical characteristics. Next, we're going to explore the reactions of alcohols. Here, we're going to focus on the oxidation reactions of alcohols, how alcohols can be converted into mesylates and tosylates, and their role in protecting groups. Finally, we'll wrap up with the reactions of phenols. Now, alcohols, they have the general formula ROH, where R represents a hydrocarbon group, and OH is the hydroxyl functional group. This hydroxyl group is what defines alcohols and what gives them their unique chemical and physical properties. When we're naming alcohols systematically using IUPAC nomenclature, the longest continuous carbon chain containing the hydroxyl group is chosen as the parent structure. Then the name of the corresponding alkane is modified by replacing the E ending with OL to indicate the presence of an alcohol. For example, if we start with propane and we replace one hydrogen with a hydroxyl group, the name changes to propanol. Then it's important to number the carbon chain in such a way that the hydroxyl group receives the lowest possible number. So for this molecule, the name is 2-propanol. In 4,5-dimethyl-2-hexanol, the longest carbon chain is 6 carbons long, and the hydroxyl group is on carbon 2, and then the 2 methyl groups are on carbons 4 and 5. So here, numbering in this way ensures that the functional group takes priority and that the substituents are correctly positioned in the name. Aside from the IUPAC method, there is also a common naming system where alcohols are named as alkyl derivatives followed by the word alcohol. This is frequently used for simple alcohols. For instance, ethanol is often referred to as ethyl alcohol, and 2-methyl-1-propanol is commonly called isobutyl alcohol. In cases where the hydroxyl group is not the highest priority functional group in a molecule, then it's treated as a substituent rather than the main functional group. In such cases, the prefix hydroxy is used instead of the OL suffix. This happens when other functional groups, like carboxylic acids, aldehydes, or ketones, are present because they take precedence in nomenclature. For example, if a compound contains both a hydroxyl group and a carboxyl group, the carboxyl group dictates the name, and the hydroxyl group is treated like a substituent. So it's referred to with the hydroxy prefix rather than being the primary functional group in the name. Finally, let's talk about phenols. This is a special case of alcohols where the hydroxyl group is attached to an aromatic ring, specifically a benzene ring. Unlike regular alcohols, phenols exhibit distinct chemical properties due to the influence of the benzene ring. One of the most notable differences is their acidity. While typical alcohols are not very acidic, phenols are significantly more acidic because their conjugate base is stabilized by resonance. This means that when a phenol loses a proton, the resulting negative charge on the oxygen can be delocalized across the benzene ring, and this spreading out of the charge results in a more stable conjugate base. So as a result, phenols are more likely to donate a proton compared to regular alcohols. Another key feature is their ability to form substituted derivatives, where additional functional groups are attached to the benzene ring. The positioning of these substituents follows a specific naming system based on relative positions on the ring. So the ortho position, it refers to a substituent located adjacent to the hydroxyl group. The meta position refers to a substituent one carbon away from the hydroxyl group. And then the para position refers to a substituent located directly opposite the hydroxyl group. Understanding these positions is crucial when naming substituted phenols. As a side note, the ortho, meta, and para system is a general naming convention that's used for di-substituted benzene rings, not just for phenols. Now, one of the key properties that make alcohols unique is their ability to form intermolecular hydrogen bonds. This interaction occurs because the hydroxyl group contains a highly electronegative oxygen atom, which creates a partial negative charge on oxygen and a partial positive charge on the hydrogen it is bonded to. As a result, the hydrogen of one alcohol molecule is attracted to the oxygen of another, forming a hydrogen bond. This strong intermolecular attraction significantly increases the boiling points and melting points of alcohols compared to similar hydrocarbons that lack hydrogen bonding. To understand why this happens, it helps to compare the nature of intermolecular forces versus intramolecular forces. Intermolecular forces are weak interactions that occur between molecules, holding them together in the liquid and solid states. Examples of intermolecular forces are dipole-dipole, hydrogen bonding, and London dispersion forces. In contrast, intramolecular forces like covalent bonds are the strong forces that hold atoms together within a single molecule. While covalent bonds dictate the chemical identity of a molecule, intermolecular forces play a crucial role in determining physical properties such as boiling point, melting point, and solubility. The stronger the intermolecular forces, the more energy is required to separate molecules from each other, leading to higher boiling points. Now, hydrogen bonding, it is a particularly strong type of dipole-dipole interaction that occurs when a hydrogen atom is covalently bonded to a highly electronegative atom like oxygen, nitrogen, or fluorine, and it then interacts with another electronegative atom on a neighboring molecule. In the case of alcohols, the hydroxyl group is responsible for this strong hydrogen bonding, which explains why alcohols have a much higher boiling point than hydrocarbons of similar molecular weight. Then with added hydroxyl groups, the boiling point also increases. Aside from boiling points, alcohols also exhibit varying degrees of acidity, which can be analyzed by looking at their dissociation in water. In general, alcohols are weak acids, meaning they do not readily donate protons in solution. This is because the conjugate base of an alcohol is not as stable as other conjugate bases like those of carboxylic acids. However, different alcohols have different acid strengths, which we can compare by examining their pKa values. For example, water has a pKa of 14, meaning it is a very weak acid. Methanol is slightly less acidic with a pKa of 15.5, while ethanol has a similar value of around 15.9, making it an even weaker acid. However, phenol is an exception. It has a significantly lower pKa of around 10, meaning it is much more acidic than regular alcohols. This increased acidity is due to resonance stabilization, in which the conjugate base of phenol is able to delocalize the electron density. So when phenol loses a proton, the negative charge on oxygen is delocalized across the benzene ring, making the ion more stable and the acid stronger. In summary, alcohols are defined not only by their hydroxyl group, but also by the strong hydrogen bonding interactions that give them unique physical and chemical properties. Their boiling points are influenced by intermolecular forces, and their acidity varies based on molecular structure, with phenols standing out as significantly more acidic than simple alcohols. With that, we can now move into Objective 2 and discuss the reactions of alcohols. Alcohols are versatile functional groups that participate in a variety of chemical reactions. One significant transformation of alcohols is oxidation, which can produce a range of different products depending on the structure of the alcohol and the choice of oxidizing agent. Primary alcohols can be oxidized to aldehydes when treated with PCC. This is a reagent that selectively stops oxidation at the aldehyde stage. However, under stronger oxidative conditions, such as with chromic acid or Jones oxidation, primary alcohols can undergo further oxidation to produce carboxylic acids. This ability to control the extent of oxidation allows for selective synthesis of different functional groups based on reaction conditions. In contrast, secondary alcohols are oxidized to ketones because they lack the additional hydrogen required to undergo further oxidation to a carboxylic acid. This transformation is commonly achieved using dichromate salts, which serve as strong oxidizing agents. Now, something important to point out is that tertiary alcohols do not undergo oxidation under normal conditions because they lack the necessary hydrogen atoms on the carbon bearing the hydroxyl group. Beyond oxidation, alcohols can be modified to enhance their reactivity in nucleophilic substitution reactions. In their native form, hydroxyl groups are poor leaving groups, meaning they don't readily depart in reactions like SN1 and SN2 substitutions. However, alcohols can be converted into mesylates and tosylates, which are much better leaving groups due to their resonance stabilized structures. This transformation makes alcohols more reactive in substitution reactions, and it allows them to be displaced by nucleophiles efficiently. Another important application of alcohols is their role in protecting groups, particularly in the context of carbonyl chemistry. Carbonyl compounds, such as aldehydes and ketones, are highly reactive, and that makes them susceptible to undesired reactions under certain conditions. So to prevent this, carbonyls can be temporarily protected by reacting them with two equivalents of an alcohol or a diol, forming acetyls or ketols, respectively. These functional groups are stable under basic and neutral conditions, and they effectively hide the reactive carbonyl from unwanted transformations. Then when protection is no longer needed, they can be deprotected, and that will regenerate the original carbonyl functional group. And this regeneration is achieved by treating the compound with aqueous acid, which will hydrolyze the acetyl or ketyl back into the original aldehyde or ketone. To better understand this process, let's work through a quick example. So what you see here is we begin with a molecule that has a ketone and an ester functional group. Because ketones are susceptible to reduction, we first need to protect the ketone before proceeding with any reductions. So to do this, we react the ketone with a diol in the presence of an acidic catalyst. This reaction then converts the ketone into a ketyl, which is much more stable under reductive conditions. So then, the newly formed ketyl prevents unwanted reactions at the carbonyl site while allowing us to selectively target other parts of the molecule. So with the ketone now protected, we can proceed with reduction. The next step involves treating the compound with lithium aluminum hydride, which selectively reduces the ester group into an alcohol. Importantly, the ketyl remains untouched during this reaction, and that prevents the ketone from being reduced. Once the desired reduction is complete, we can then regenerate the ketone by removing the protecting group, and this is done by treating the compound with aqueous acid, which hydrolyzes the ketyl back into the original ketone functional group. The reaction essentially reverses that initial protection step, and it leaves us now with a ketone and an alcohol as the final functional groups in this molecule. So by carefully applying these transformations, we achieve selective reduction of the ester without affecting the ketone. If we had not protected the ketone and just directly used lithium aluminum hydride, we would have reduced both the ketone and the ester group. Now we can move into our final objective. Here we're going to discuss reactions of phenols. Phenols undergo unique reactions due to the presence of the hydroxyl group directly attached to an aromatic ring. One of the most important transformations of phenols is oxidation, which leads to the formation of quinones. Quinones are a class of compounds that are characterized by their conjugated diketone structures, and they play critical roles in both chemical synthesis and biological processes. The oxidation of phenols typically involves the use of strong oxidizing agents, such as sodium dichromate in sulfuric acid. When 1,4-dihydroxybenzene is treated with these reagents, the hydroxyl groups are oxidized into carbonyl groups, producing 1,4-benzoquinone. The name of a quinone is derived by indicating the positions of the carbonyl groups numerically and then appending quinone to the name of the parent phenol. Due to their extended conjugation, quinones are highly resonance stabilized electrophiles, and that makes them chemically reactive and very useful in chemistry. This property makes them essential in biochemical pathways such as cellular respiration. For example, vitamin K1 and vitamin K2 are biologically active quinones that play a vital role in blood clotting and electron transport. In addition to quinones, hydroxyquinones can be formed by the further oxidation of quinones. These compounds retain the quinone core structure, but they contain one or more hydroxyl groups attached to the ring. While they share similar conjugation and electrophilic properties, the additional hydroxyl groups influence their solubility, their redox potential, and their reactivity. Examples include 2-hydroxy,1,4-benzoquinone, and tetrahydroxy,benzoquinone. These are more polar and they have distinct biological roles compared to their parent quinones. Now, one of the most important biologically active quinone is ubiquinone, also known as coenzyme Q. Coenzyme Q is a crucial electron carrier in the electron transport chain where it undergoes reversible redox cycling between its oxidized and reduced forms. In its oxidized state, ubiquinone contains 2 carbonyl groups, which can be enzymatically reduced to form ubiquinol, where the carbonyl groups are converted into hydroxyl groups, like you see in the images comparing the two. This redox cycling allows ubiquinone to shuttle electrons between complexes 1, 2, and 3 in mitochondrial oxidative phosphorylation, and that drives ATP production and cellular energy metabolism. And with that, we've covered everything we want in this chapter. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.